And our next presenter is Carrie Mitchell. And Carrie, you have the floor.
Thank you. Let's see here. Okay, thank you. Thanks to Discovery Park, to Purdue Giant Leaps, and to the Convergence conveners for this opportunity to share the vision and the excitement of our Purdue multidisciplinary team in our efforts to assist this nascent growth industry, the indoor agriculture industry, which typically locates in communities that are urban or para-urban. They struggle right now with high upfront capital costs, high operating expenses, and they have a fairly deep carbon footprint from the electrical costs they incur for controlling the environment within these repurposed warehouses, where typically leafy green and culinary herbs presently are grown. That is the present preference for the indoor vertical farm industry. So we envision that industrial food waste that is produced in copious amounts in para-urban and urban communities can be, it's very energy rich, and it can be processed all the way to through anaerobic digestion to electrical generation, and offset some of the very high electrical costs that presently are incurred in indoor agriculture. As well, there's a lot of food waste from the consumer market, which includes both the food service industry as well as all households. So they're all contributing to this. And so we would propose a partial closure of carbon and energy loops to help this industry. Right now, of their total operational costs, about 30% is for energy, especially electrical. So typically, as I said, they are developed in repurposed warehouses, often abandoned warehouses in urban areas. And they typically will be stacked in tiers up to 12 high. This one in Newark, New Jersey happens to have 70,000 square feet of active production space on a continuous basis. And they are quite productive, but they will spend many hundreds of thousands of dollars per year just in paying the electrical bill from their grid use. So it's a real issue, and energy is one of the areas that we think we can make some inroads by coupling it with this food waste issue. So the current practice is to have an open vertical farms with the vents open. They're bringing in fresh air, they're venting out air. And one of the reasons for this, when you fill buildings with vegetation like that, it becomes extremely humid from transpiration by leaves in the light, and this can create physiological problems. So they have to vent it out or do something for dehumidification. And there can also be thermal control issues. So they often have the vents open, and as well, carbon dioxide, which technically is a trace gas in the atmosphere, being measured in parts per million quantities, but taken up by plants in substrate amounts by plants during the photosynthesis process. If you fill a warehouse with vegetation like you saw in the previous slides, you can draw the carbon dioxide down in that building, and the crops will actually stop growing, even if you're giving them good nutrition, water, light, whatever. So typically they have to resort to injection and control of pure CO2 to supplement the that which is brought in through normal natural ventilation. And inadvertently, you will lose some of even that injected CO2 in the process. So it's anything but sustainable. So as the industry struggles, we look at ways that we might be able to overcome this. And so at the heart of our proposal is that we would close the system partially with respect to mass. So, and then we would use electrical energy not only for generating electricity to power more or less, but improving energy efficient LED lights, but also to condense the water vapor from transpiration back to liquid water and recycle that back to hydroponics, okay? And as well take care of the thermal load in the building from electrical generation. And then using all phases of the anaerobic digestion process, we would generate not only energy-rich methane that then could be combusted in microturbines to low voltage direct current that could drive the LEDs, but also some of the CO2 byproducts could be cleaned up and then injected into the building. We would not likely replace the requirement for all grid or all CO2 injection, but see what the systems analysis tells us and whether it will be profitable to do so. So within our current Purdue team, Michael Delgado handles the econometrics. Abby Engelberth does what I've been talking about here. She works with food waste and value-added products. Andrew Flax will look at the social implications of closing loops with waste materials on various communities. Haiji Kim, an expert on water and nutrient efficiency and recycling and reclamation of these things. I work on leveraging unique physical properties of LEDs for greater efficiency of lighting. Joe Sinfield handles business and systems analysis metrics, and George Zhao works on wastewater reclamation, recycling, and all of these people interact. They cross over for crossover innovations that are used. And our long-term vision then is to see more sustainable, closed indoor ag operations in every urban area worldwide. Thank you.
Cary, thank you so much. We have time for some questions.
Yes, sir.
Well, it's interesting what you described actually is related to space programs, closed ecological systems, closed ecosystems. And I'm aware that back in the former Soviet Union, started from the Korolyov's time, they actually worked on this for space trips, closed ecological system. And similar program was here in Arizona somewhere.
Yes, yes.
It's very much related. And of course, bringing it to houses.
Right, and a couple of centers here at Purdue dedicated to that. And that's where I got my inspiration for doing this with respect to ground-based agriculture, especially back in 2006 when NASA put all of this cells and ALS and N-SCORT work on the back burner, from which they haven't completely recovered yet.
Any other questions for Cary? There's one out there.
You described your work in LEDs for plant lighting. What's the spectrum for LED frequencies that's optimal for, say, growing herbs?
Yeah. For this proposed project, we will focus on close canopy lighting, targeted lighting, and phasic optimization, where some of that spectra and intensities and interactions with carbon dioxide will be interacted. We're projecting we can drop the present costs of electricity for lighting somewhere between 50 and 90% from where they are. And the second part of your question is we started out with photosynthetically active radiation, red and blue, and all the other wavelengths are now being added back. It's almost like we're rediscovering white light.
Thank you, Cary.
Sure.
Okay.